Right now we're going to talk about feedback, start with an overview, block diagram, motivation, then get into some circuit examples with op amps specifically, and along the way we're going to have some key takeaways, such as feedback reduces the gain, but what you gain from that trade-off is stability, linearization, and we'll also notice a gain bandwidth product trade-off. So your bandwidth increases as you reduce the gain. So let's start with the background to block diagrams. For electronics, we're typically interested in amplifiers, and A of the amplifier is an active element. So BJT, MOSFET, op amp, current gain, voltage gain, all that sort of stuff. And one problem you have with just assigning an input to an output through this gain is the gain is not constant across batch of device produced, frequency, temperature, etc. So what you want to do is keep some gain, but you want to make it more reliable and not dependent on your frequency or the batch variation and stuff like that. So the solution is to introduce elements that are more stable across all of these at the expense of some of the gain. So for example, here with the BJT, our gain is coming from the current gain. So we want to keep IC at some quiescent value. So the collector current, we want to stay relatively constant, even though the beta of this transistor might be changing slightly based on device or temperature or whatever. So we'll see as, let's say beta increases for whatever reason, say it's heating up. Well, that'll increase the collector current since IC is beta times the base current. But increasing the collector current also increases the voltage across this resistor here. And if that voltage increases, then VBE decreases because we're assuming the base voltage is constant. And since VBE decreased, that means IB will decrease as well. And there we have it. Since IB decreased, the quiescent collector current will also decrease. For an op amp example, let's say we have one op amp with a intrinsic gain here of 1,000,000 or 100,000. So say we're swapping out an op amp from 100,000 to a gain of 1,000,000. And recall op amp amplifies the difference between the positive and negative terminals here. We'll call that voltage E for error. And if A increases, the output voltage will increase because we're not changing this voltage, but the gain is increasing. But increasing that voltage will also increase the voltage across V1. Voltage division, V1 is V out times R1 over R1 plus R2. And if V1 increases, then the difference between the positive and negative terminal decreases, thus decreasing the gain. So where's the feedback in these circuits? Well, feedback for here is this emitter resistor, and the feedback here is typical op amp feedback we're used to. And in fact, that means we have to change our block diagram to include feedback. So we not only have an input source XS, but we have some feedback that's going to be subtracted from that to give us our true input to the active device here. And we're going to include another block, beta, which is the passive network that's feeding back some portion of our output. So for electronics, we're only interested in negative feedback for op amps for the most part. For oscillators and such, positive feedback is important. Schmidt triggers and comparators and stuff, but for this video, we'll stick with negative feedback. And that means that at the summing terminal, we're subtracting the feedback voltage. For positive feedback, we'd want to add in this feedback voltage. And let's try to come up with an expression for the output over the source input here. So we have three equations here, and you can go through those on your own, but if we sub them into one another, we're left with this equation here. And in practice with op amps, let's take op amps for an example. A, we already said was about 100,000, or a million or something. And beta is the voltage we're feeding back. We're not going to be with resistive dividers. The minimum we're going to have is about 1,000th. You know, if this is an ohm and a kilo ohm, you know, even that's pushing it. So at worst case, we can say that this product of A beta, is about 100. And in that case, 100 versus 1, we can ignore the 1. We're left with A over A beta. And that means our transfer function is 1 over beta. So we've essentially desensitized the output to any intrinsic gain of the op amp. So it's not dependent on A at all. It's only dependent on the resistive network we have around it, which is what we're used to when we're talking about op amps. So here's a sample non-inverting configuration here. Let's say beta is the feedback voltage we're feeding back to the input, which by resistive voltage division is just R1 over R1 plus R2 for the feedback over the output. And we're calling that 1 over, so if that's beta, then 1 over beta is 1 plus R2 over R1, which is the equation we're used to for non-inverting op amps. And let's see something else important about op amps. That large gain of 100,000 or so is only for really low frequencies. Most op amps have internally compensation capacitors that give us a dominant pole at low frequencies. And the reason for that is if we look at kind of a Bode plot for uncompensated or compensated op amps, if we have a compensated op amp, we're going to roll off our gain, which means we're going to get rid of some of these other poles that are due to just parasitic capacitances inside of the op amp. And here's the dark black line is their phase response. We'll see we'll have just one single pole response that'll really delay our phase movement until we get our gain down pretty low. So in this example, when the gain hits 0 dB, we still have about a 45-degree phase margin. Notice this axis is, they're plotting phase margin, not just phase shift. But if we look at the uncompensated, in this example, we have all these extraneous poles out in the kilohertz, 100 kilohertz, megahertz. And by the time the gain gets to 0 dBs, our phase shift is already at 180, so we have 0 phase margin. So when you internally compensate your op amp, you're making it more idiot-proof, but you're also getting rid of some of the gain that you could have had. So there's a good trade-off, and in a later video I'll show differences between compensated and uncompensated on the scope. But for now, let's look at what we have here, and we'll just assume we have a dominant pole, a compensated op amp, where you can kind of assume the transfer function is some constant over a single pole, which is this here, one single pole roll off. And if we do that, we can plot our gain versus frequency. But this is pretty useless for normal circuits. What we really want, if we want to have some non-inverting op amp, is we want this to give us this gain at all frequencies, not just limited to 10 hertz and then we get a bunch of attenuation. So let's see how actually adding this feedback really does give us this response regardless of frequency. And here we'll go through the math of it. So here we're starting out with our A of S as the op amp single pole transfer function. And what we're going to do to that is call that A of S. We'll just arbitrarily assign a mega naught as 10 radians per second, which is the single pole cutoff. And capital A naught, which is the intrinsic gain at low frequency, to just be 1,000,000. And we're going to define a new transfer function, G, which is the output over the input with our beta feedback here. And we're going to define 1 over beta as 1 plus R2 over R1, because that's what our non-inverting op amp configuration is. And we'll call that G naught, because that's what we want to have our constant gain at for most of our frequencies. So here A naught is our constant gain region. We want G naught to be lower, you know, around 10. We're going to call this 1 plus R2 over R1, 10. And we're going to see how the trade-off between gain and bandwidth mathematically happens. So if we just look at our equations here, V naught is A of S times E. We can have an equation for E now is V in minus this voltage that we have from voltage division. And we can plug them into each other, see this, and we're left with this kind of beast here where we have A of S over 1 plus A of S over G naught. So if we multiply numerator and denominator by the same thing, we can try to simplify this out. And the simplest we can get is here. And what we notice here is if G naught is 10 and A naught is 1,000,000, we can just ignore this term completely. And what we're actually left with is another standard transfer function form of some constant over 1 plus S over some cutoff frequency, where in this case our cutoff frequency, big omega naught, we have is little omega naught times big A naught over G naught. And if we actually go back and look what those quantities are, remember omega naught was our pole of our compensated op amp, big A naught is our million intrinsic gain, and G naught was our created 10 voltage gain from our inverting or non-inverting op amp. We see that if we define this as big omega naught, we have a gain bandwidth trade-off. So if we take big omega naught times G naught, so bandwidth times gain equals bandwidth times gain. So no matter what our network is, we're always going to have this trade-off where low frequency constant gain times the bandwidth, or where the 3 dB point is, that product will always be equal. And here's just it plotted. Now we have our cutoff frequency, big omega naught, of this was 10 over 10 times 1,000,000, so that equals 1,000,000, and that's as we expect from this graph. And notice we could also derive this just from a feedback formula we proved earlier, where we have the feedback equation is A over 1 plus A beta. And that's exactly what we have here. A over 1 plus A beta, which we defined here as 1 over G naught.